So we want to find out the convergence of these series, namely summation 1 by n and summation 1 by n square to start with. It is slightly tricky, but this can be shown to be pi square by 6. So summation 1 by n square converges. It is quite a interesting result, although beyond our calculus discussion, but you can actually show that summation 1 by n square is pi square by 6. So we want to basically uh, find out, compare 1 to infinity of dx by x square and summation n equals to 1 to infinity of 1 by n square. So to make this comparison, let's do the following. So let's basically have the following. We have let's make these rectangles. These rectangles have base basically 1, and the height is given by the function values at these points. Okay, so we are looking at the right hand Riemann sum here. So we are looking at these areas. So the area of the first one is going to be 1 times the base times 1 by, what is the function value? The function value is given by the value at the right hand point, which is 2. So 1 by 2 square. Similarly, this other one is going to be 1 times 1 by 3 square. And then we keep on going forever. This is going to be less than the actual area, which is given by area below this curve, right? So the area below this curve is this whole area. And clearly this area is bigger than the area of the sum of the rectangles, right? So okay, so what we have is that this area is less than 1 to infinity of 1 by x square dx. Right. Now, if you identify this, this can be written as summation n equals to 2 to infinity 1 by n square, that is less than integral 1 to 1 by x square dx. So let's evaluate this integral first. So this integral is an improper integral of type 1. So if you recall, this is going to be limit as t goes to infinity 1 to t of 1 by x squared dx. And after integrating, you can see that this is going to be limit as t goes to infinity minus 1 by x 1 to t, and that is going to be limit as t goes to infinity minus 1 by t plus 1, and as t goes to infinity, this is going to be 1. So if I add 1 on both sides here, I will see that summation n equals to 1 to infinity of 1 by n square is less than equal to 2. Yeah. So therefore we can say that now note that summation 1 by n square is, if you look at Sn, which is a sequence of partial sums, 1 plus 1 by 2 square dot 1 by n square. So now this is an increasing, this is a monotonically increasing sequence, right? Because Sn plus 1 is bigger than Sn, because after all, you're adding one term extra to it, right? Which is 1 upon 1, 1 by, so you're adding 1 upon n plus 1 square, right? In Sn plus 1. So Sn plus 1 is bigger than Sn. So therefore, this sequence is monotonically increasing, it's bounded above by 2. Therefore, Sn converges by what? By monotone theorem test, or monotone sequence. By theorem 1, monotone sequence bounded above monotone increasing sequence bounded above converges. So that's the idea. So therefore this series converges. So this guy converges. Now we can have the similar argument for 1 by summation 1 by n and dx by x. So notice the following. So in this case, I'm going to work with the left-hand points for the height and so on. So you can see the sum of rectangles, sum of areas of rectangle is what? Summation. So what is the height here? So base is again 1, 1, 1 for all of these. The height for the first part is given by 1 by n because the function is 1 over x. So at this point, the height is given by 1 by x. At this point, the height will be given by 1 by 2, right? So it's going to be 1 plus 1 by 2 plus 1 by 3 for the height here, right? So this basically 1 by 4 for the next one, so on and so forth. And this is going to be greater than the actual, since it overshoots the area under the curve, this will be greater than integral 1 over x dx. So now let me write down this summation. So I have summation n equals to 1 to infinity of 1 by n is greater than limit as 1 goes to infinity of 1 by x dx, right? So what do we have? What is limit as n goes to, so what is integral of 1 to infinity of 1 by x dx? That is same as limit as t goes to infinity of 1 to t of 1 by x dx, which is going to be limit as t goes to infinity of ln x from 1 to t. That is going to be limit as t goes to infinity of ln t minus ln1. And as t goes to infinity, this guy will go to what? Infinity. And this is the leading to this diverges, right? So therefore, what do we get? We get summation t1 by n diverges. So here you see a relationship between an integral and the series. Yeah. So this is what is called as integral test. So we can use integrals now to connect. So we are connecting integral with the series, right? So this connection is called integral test. You'll see that in a minute. So let f be continuous. It should be positive and decreasing function on 1 to infinity, and let an be f of n, right? Let's go back to the original one. We had, for example, if you're looking at summation 1 by n square, you were looking at what? F of x equals to 1 by x squared. So this function on 1 to infinity is continuous, right? It's a rational function. Rational functions are continuous on their domain. The domain of this function is all real numbers except 0. So in particular, it's continuous on 1 to infinity. It is positive because all the inputs are positive and you're squaring, so it's going to be positive. So 1 over x squared is positive. It is decreasing, that you can check by derivative. And what do you have? You have an is f of n, which was what? 1 by n squared. So then we have a connection between summation 1 to infinity of 1 by n squared and 1 to infinity of 1 by x squared dx. We saw that this is convergent, and hence this was convergent. Although we did not use the integral test while proving it, we used the bounding on this in series. So, but bigger part is true. So let's look at this test again. So suppose f is continuous, positive, and decreasing on 1 to infinity, and let a n be f of n. So this was the scenario in this case. Then series summation n equals to infinity a n converges if and only if. That means it's both ways. So if this series converges, then this integral 1 to infinity f x dx converges. And vice versa, if this integral converges, then this series converges. Okay. So this is what is written here. If 1 to infinity fx dx is convergent, then summation n equals to 1 to infinity of an is convergent. And if this guy is divergent, then this guy is divergent as well. Okay. So this test is called integral test. So now let's basically see the following problem. So summation n equals to 2 to infinity 1 by n times ln n squared. We want to basically see, we want to apply the integral test on it. So let's see, can we first apply integral test? So what function we'll choose? We'll choose f of x to be 1 upon x into ln x squared. Now this is continuous on, so note that you're starting from 2, so this is continuous on 2 to infinity, right? It is also positive, right? It's positive as well. Why is it positive? Because on 2 to infinity n is positive, and ln n is also positive, right? Ln x is also positive because ln x is greater than equal to, is strictly greater than 0 on where, as soon as you pass 1, right? Because ln 1 is 0. So as soon as you pass 1, it's going to be greater than 0. So in particular, it's going to be greater than 0 on 2 to infinity. So if you take reciprocal of a positive function, you get a positive function. So it's continuous positive. And the third thing we need is that it should be decreasing. So for that, let's take the derivative of this. So what is f prime x? So we need to show that the derivative is less than 0. So let's compute the derivative. So we'll use the chain rule. So this is going to be n ln n, sorry, x ln x square, the whole square, with a minus 1 multiplied by derivative of x ln x, which is going to be a derivative of x ln x square, right? This is a chain rule. So therefore we get minus 1 upon x ln x square, the whole square. And what is the derivative of this? Let's do the derivative. So x times 2 ln x divided by x plus derivative of this ln x square. Now note that these guys are positive. This is positive. This is positive. So you have one negative sign. So this means what? This is less than 0. Therefore, what? F is decreasing on 2 to infinity. And what else do we have? We have f of n equals to an. Therefore, we can apply integral test. So the integral now will decide whether the series converges or not. Can apply integral test. So let's apply the integral test. So what is the integral of 2 to infinity of 1 by x ln x square dx. So now here we have to use, so this is going to be limit as t goes to infinity. Now what is integral of this guy? Integral of this is going to be minus 1 upon ln x. 2 to t, that is going to be limit as t goes to infinity. Now this is going to be minus 1 by ln t plus 1 upon ln 2. And as n goes to infinity, this will go to, this part will go to 0. So therefore you get 1 upon ln 2. So what is the upshot of this? Upshot is, this implies the series converges. And what test are we using here? We are using the integral test, using integral test. So now we want to basically use integral test to test the P series for the convergence. So what are P series? So P series are essentially series of form which are written as summation n equals to 1 to infinity 1 by n to the power p. So these are called P series, obviously, but the name is obvious because the power is p there. And we want to basically see that, we want to see, does it converge, all right? Or does it converge for some p at least? Because we already know if n is 1, it diverges because you get a harmonic series, right? And if n is 2, it converges. So we have already seen if p equals to 1, diverges, and if p equals to 2, it converges. But rather than doing it for every p, every number, not just for integers, but for even for real numbers, let's deal with this problem in generality. Okay. So consider f of x equals to 1 upon x to the power p. And here we are considering p greater than 0. Yeah. Because if p is less than equal to 0, if p is less than or equal to 0, limit as n goes to infinity of 1 by n to the power p is what? Is either 0, sorry, either infinity or it's 1. Yeah. So by divergence test, it diverges. Yeah. What do I mean by it? I mean the series. The p series diverges. So that is not our interest. Our interest is when p is greater than 0. So consider this function on 1 to infinity. So this function is continuous and positive on 1 to infinity. Now we need to see if it is decreasing or increasing. So let's take f prime x. F prime x is going to be, derivative of this is going to be minus p upon x to the power p plus 1. Now the bottom is positive, but minus p basically makes this as less than 0. This implies f is decreasing on 1 to infinity. And also note that f of n equals to 1 by n to the p, which is an. So therefore we can apply integral test. Okay. So we want to apply integral test So how do we apply integral test? So we need to find this integral 1 by x to the p dx. Now, what about this integral? So this integral is same as limit as t goes to infinity, integral 1 to t of 1 by x to the power p dx. All right. Now, if you compute this integral is going to be first limit as t goes to infinity. Now, if p is equal to 1, we have already seen it, but let me just write down anyway. If p is 1, I get what? ln x from 1 to t, limit as t goes to infinity. And if p is not 1, then this integral is going to be what? X to the power minus p plus 1 upon minus p plus 1, integral 1 to t. Okay. Now note that if this power is positive, okay, let me just rewrite it again. So this is going to be limit as t goes to infinity minus t. So we have t to the power minus p plus 1 upon minus p plus 1 minus, and then I put 1, so I get 1 upon minus p plus 1 if p is not 1, and it is ln t minus ln 1 if p is equal to 1. Now note this carefully. So as t goes to infinity, this will go to infinity or 0 depending on what power of t is, right? So if you have t to the power minus 1, you take limit as t goes to infinity, you get 0. Because then you have 1 over t. However, if you have t to the power anything positive, so if you have t to the power anything k, if k is greater than 0, then this is going to be infinity. If k is less than 0, then it's going to be 0 if k is less than 0, right? Because then it becomes 1 over positive power and that goes to 0. So this guy, so the first one, so from here, what do I get? I get if 1 minus p plus 1 is less than 0, then what will happen? Then we will have, if this is less than 0, then there will be a convergence, right? So this then what? Then limit as t goes to, then the limit is equal to, so I'll break this again. This is equal to minus 1 upon minus p plus 1 if p is what? If 1 minus p plus 1 is less than 0. And infinity if minus p plus 1 is greater than 0, or from this part we'll get p equals to 0, p equals to 1. So this would imply p 1 is less than p, or if 1 equals to p, then what happens? There's a divergence. Otherwise it converges. So that is same as saying here, if you rewrite this, this is same as 1 is, and here we get what? We get p is what? Less than equal to 1, right? So if p is less than equal to 1, it diverges. If p is greater than 1, then it converges. So we get the p series test. So summation 1 by n to the power p converges if p is greater than 1, diverges if p is less than or equal to 1. So this is called p series test. So now the next question is the following. Suppose I have a series summation n equals to 1 to infinity an, and this series sum is s, so it's a convergent series. And then in that case, we want to define the n remainder, or nth remainder is take s minus sn. That is going to be an plus 1, because sn is a1, a2, dot, 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 an. So Sn minus S is going to be an plus 2, dot, dot, dot. Now, what are we trying to do? We are trying to estimate the series using partial sums. That means what? Instead of computing, my series sum is this infinite sum. Can I approximate it by sum Sn? Right? That's the idea. But whenever you do an approximation, an error will creep in, and you want to estimate then how much the error is. All right? Is it reasonable to have that kind of error? Yeah. Or is it reasonable to accommodate that kind of error? Right? So for that, we have the following. So suppose you have a function f of k equals to ak, where f is continuous positive decreasing for x greater than equal to n, and summation an is convergent. Then if your Rn is between s, then your Rn is s minus Sn, right? That is what the definition is. So in that case, we have the following estimate for Rn. The estimate for Rn is, it is between n plus 1 to infinity of f of x dx and n to infinity of f of x dx. So Rn is sandwiched between these two guys. Okay, so that is so your Rn is going to be sandwiched between these two integrals. Okay. So let's do a problem on this. So determine in the previous example, we have shown that series converges, right? And so we have already know that this converges and it satisfies all of these, right? What is needed to estimate the remainder, that what it's continuous, positive, and decreasing for x greater than equal to n, and we know that this is convergent. Now we want to estimate. So what is the problem asking us? The problem is asking us, determine how many terms do you need to find the value of this sum accurate up to 0.01. So accurate up to 0.01 means your Rn should be accurate up to 0.01. So let's work on this. So we want basically Rn to be less than what? 0.01. Yeah. So this is what we want. Actually, we generally want absolute value of Rn to be less than 0.01. But note that this series is positive, right? So Rn is going to be, you have Rn is, this is your Rn, right? And these all terms are positive, right? Because you are looking at series with positive terms. So therefore, it makes sense to just concentrate when is Rn. So determine how many terms you need to add so that you get value of the sum accurate within 0.01. So you want to find n such that Rn is less than 0.01. So that's what this problem says. That is, how large must n be for the remainder, it's not reminder, it's remainder, to satisfy the inequality Rn is less than 0.1. So let's work on this. So we have the following. So your Rn is going to be between these guys, right? So let me use this formula. So Rn is going to be between n plus 1 to infinity of 1 by n ln n square dx. Your Rn is sandwiched between this guy and, so you can see that sandwiched between these guys. 1 by n. So it should be x, right? X ln x ln x square dx. So this is what your bound on Rn is. So your Rn is bounded and it is basically less than equal to sign. So this is going to be, this is the bound on Rn. So let's try to see how to find Rn in this case. So if you look at this integral, what is this integral going to be? So we have already computed that this side, the integral is going to be ln of, let's go back to the computation. There's no point of repeating the computation. So here we have already done the computation of this integral. The integral was -1 by ln x 2 to t, right? So in this case, the integral is going to be minus 1 by x ln x from n plus 1 to t, limit as t goes to infinity. This is your Rn is between this guys, limit as t goes to infinity, s goes to infinity of what? N to s, and we have already done the computation here. So -1 upon ln x, the limits are from n to s. So this is going to be, if you compute this, is going to be 1 upon ln n plus 1 is less than Rn is less than equal to 1 upon ln n. So this is what we want. So what is your Rn? What is the remainder? So you want remainder to be less than 0.01. So essentially you're not worried about the lower part, but you want immediately, you want this to be true. Therefore, what do we get? We get ln n is less than equal to 1 upon 0.01, which is going to be 1, 0, 0. Right? So you're looking for when is ln n greater than 100. Sorry, you have, so you're basically taking a reciprocal on both sides. So you're asking when is what here. So we have this guy. So your Rn is less than this. So you are bringing this here. So what do we get out of this? So when is ln n equals to what? When is ln 1 equals to 100? So can we do this computation? What your n is going to be, right? Roughly 2.69 times 10 to the power 43 is your bound on n.